Scientists still can't quite believe what the James Webb Space Telescope just captured, because sitting in the data is a real, direct image of a planet orbiting another star. A planet whose atmosphere Webb then went on to read in a level of detail nobody thought would be possible this soon. Stick around and hit subscribe right now, because tonight we're walking through exactly what that image shows, why it matters so much more than a simple photograph, and everything Webb has uncovered since. This is not some minor footnote buried in a scientific journal. This is one of the clearest windows humanity has ever had into a world beyond our own solar system. And by the time we're done, you'll understand exactly why astronomers are still talking about it. Before we get into the image itself, I want to be upfront about something, because good science deserves an honest setup rather than an exaggerated one. Webb was not literally the first telescope in human history to capture an image of a planet orbiting another star. That milestone actually happened back in the mid-2000s, when ground-based observatories managed to capture faint, blurry, direct images of a few young, glowing gas giants orbiting at extreme distances from their stars. Those were real, genuine breakthroughs at the time, but they were also exactly what you'd picture when you hear the phrase blurry and distant. A handful of smudged pixels, a whisper of light captured only because those particular planets happened to still be blazing hot from their own formation, and sitting far enough from their star's glare to be teased out at all. What Webb has now done is something categorically different, and understanding that difference is the whole story here. Capturing a direct image of an exoplanet has always been considered one of the hardest technical challenges in all of astronomy, for a very simple reason. A star is almost unimaginably bright compared to any planet orbiting it, trying to spot a planet's faint. Reflected or emitted light next to its parent star is a bit like trying to spot a candle flame sitting directly beside a lighthouse from many miles away. The lighthouse doesn't just outshine the candle, it drowns it completely. And any telescope pointed in that direction sees essentially nothing but blinding glare. Solving that problem required an entirely new generation of instrumentation, coronagraphs, that can physically block out a star's light with extraordinary precision, combined with a mirror large and sensitive enough to actually pick up the faint remaining signal once that glare is suppressed. Webb was built with exactly that kind of instrumentation in mind, and it put that capability to the test almost immediately after coming online. The planet in question is called HIP 65426b, and it orbits a young star roughly 350 light-years from Earth. When Webb turned its instruments toward it. In the summer of 2022, it produced something astronomers had been waiting years to see. A crisp, genuinely resolved direct image of a planet captured. Not in visible light, but across multiple infrared wavelengths, each one revealing something slightly different about the planet's glow. It was Webb's first attempt at direct exoplanet imaging, and it worked essentially on the first try, which says a great deal about how carefully this telescope was engineered. That alone would have been a significant achievement. But the image itself turned out to be only the opening chapter of a much stranger story. HIP 65426. B is enormous, roughly 7 times the mass of Jupiter, and it orbits its star at a distance more than 100 times farther out than Jupiter orbits our own sun. That distance is the detail that made astronomers sit up, because according to the standard model of how giant planets form, a world this massive is supposed to build up gradually inside the thick, swirling disk of gas and dust that surrounds a young star. That process requires a lot of raw material, concentrated relatively close to the star, where the disk is dense enough to actually assemble something this big within a reasonable time frame. Out at the extreme distance where HIP 65426b currently sits, that disk would have been far too thin and far too spread out for conventional gradual accretion to explain a planet of this size. In other words, this world sits somewhere the standard playbook says it probably shouldn't. That single mismatch has opened up a real debate in planetary science. Not the manufactured kind of debate a headline invents for clicks, but a genuine, ongoing conversation among researchers about how planets like this actually end up where they are. One leading idea is that giant planets can form closer in and then gradually migrate outward over time, nudged by gravitational interactions with other objects in a young system. Another possibility involves a different formation pathway entirely, where regions of a disk become gravitationally unstable and collapse directly into a planet rather than building up slowly grain by grain. And there's a third, more dramatic possibility that some researchers take seriously. Violent gravitational interactions in a young star system, close encounters with other forming planets, can fling a massive world outward, onto a much wider, more distant orbit than where it originally formed. None of these explanations is confirmed yet, and honestly, that's part of what makes this discovery so valuable. It's a genuine puzzle sitting in front of scientists rather than a solved case with a tidy answer, and every observatory that looks at similar systems going forward will be trying to help narrow that down. What made the image even more valuable is that it wasn't just a photograph. Webb didn't simply confirm that Hippie 65426b exists and sits where earlier ground-based data suggested. It measured the planet's brightness across several different infrared wavelengths simultaneously, which gave researchers their first real handle on its temperature and some basic clues about its atmosphere, all extracted directly from the light captured in that single set of observations. That's the real leap forward that separates this image from the blurry direct images captured 2 decades earlier. This wasn't just proof of existence, it was the beginning of an actual physical description of a world we can't visit, built entirely out of the light it emits. Since that first image, Webb has kept turning its instruments toward other exoplanets, and some of what it's found has been even stranger. Take WSP-39b, a gas giant that orbits so close to its star that its atmosphere is constantly being blasted by intense radiation and heated to extreme temperatures. Astronomers expected a fairly simple, if scorching, atmospheric profile from a planet like this. What Webb actually found was one of the most chemically complex atmospheres ever measured on any exoplanet. Its atmosphere contains water vapor, sodium, potassium, carbon monoxide, carbon dioxide, and most surprisingly, sulfur dioxide, a molecule that only forms there, through photochemistry, meaning chemical reactions directly triggered by the intense radiation coming from its host star. That detection mattered because it was the first time astronomers had captured direct evidence of this kind of active photochemistry happening in a planet's atmosphere outside our own solar system. It's essentially the same general category of chemistry responsible for building Earth's protective ozone layer, just playing out under conditions far more extreme than anything our planet experiences. Finding it confirmed that these chemical processes aren't some rare accident unique to Earth. They can occur wherever the right ingredients and the right radiation environment come together, which meaningfully broadens the kinds of worlds worth studying closely for complex atmospheric chemistry. Then there's K2-18b, a planet that became the center of a much bigger and much more contentious conversation. K2-18b is a sub-Neptune, larger than Earth but smaller than Neptune, orbiting within the habitable zone of a red dwarf star roughly 120 light-years away. When Webb examined its atmosphere, it found a thick envelope rich in hydrogen, along with clear signatures of methane and carbon dioxide, both consistent with the idea that this planet could be what scientists call a Hycean world, a theoretical class of planet with a deep global ocean sitting beneath a hydrogen-rich atmosphere. That alone made K2-18b one of the most interesting habitable zone candidates ever studied. But in 2023, a research team reported a tentative, low-confidence detection of dimethyl sulfide in that same atmosphere, a molecule that, on Earth, is produced almost exclusively by marine life. That announcement made global headlines almost overnight, and I want to be honest with you about what happened next, because this is exactly the kind of story where the follow-up matters as much as the initial claim. The original detection was explicitly described by the researchers themselves as low confidence, not a confirmed discovery, and the broader scientific community responded with the caution that this kind of claim genuinely requires. Multiple independent teams went back and reanalyzed the same. Data using different statistical methods, and several of those follow-up studies were unable to reproduce the signal with any real statistical confidence, or found that the data could be explained just as well without invoking dimethyl sulfide at all. As of the most recent published analyses, the scientific consensus is that this specific biosignature claim has not held up under closer scrutiny, and most researchers now consider it unconfirmed at best. I bring this up not to diminish how exciting the initial announcement was, but because this is genuinely how science is supposed to work. A striking result gets reported cautiously, other scientists stress test it rigorously, and the community updates its confidence based on where the evidence actually lands. K2-18b remains a fascinating, genuinely important target for future observation, and Webb will almost certainly look at it again with more data in hand. But right now, the honest picture is that we do not have confirmed evidence of life or biological activity on K2-18b, and any version of this story that tells you otherwise is getting ahead of the actual science. Proxima Centauri b tells a very different kind of story, one about the limits of what even a telescope as powerful as Webb can currently do. It's the closest known exoplanet to our own solar system, sitting just over 4 light-years away and orbiting well within the habitable zone of Proxima Centauri, the nearest star to our sun. From the moment it was discovered, it became the planet everyone wanted to know more about, simply because of how close it is. But Proxima b orbits its star at an extremely tight distance, since Proxima Centauri is a small, dim red dwarf and its habitable zone sits much closer in than our own sun's does. That proximity means the planet is essentially drowned in its star's glare from Webb's perspective, making direct imaging, or atmospheric characterization, effectively impossible with current instruments. On top of that, Proxima Centauri is known for producing powerful, frequent stellar flares, bursts of radiation. intense enough to potentially strip away a planet's atmosphere over long timescales if it doesn't have a strong enough magnetic field to protect it. So even though Proxima b is our nearest planetary neighbor beyond the solar system, and the planet most people would probably want to visit first, if interstellar travel ever became possible, it remains one of the hardest nearby worlds to actually study in any real detail. Future telescope designs, including next-generation coronagraph and starshade technology currently in development, are being built partly with exactly this problem in mind, because right now Proxima b sits tantalizingly close and almost completely out of scientific reach at the same time. The TRAPPIST-1 system offers yet another important lesson, and it's one that tempered a lot of excitement in the exoplanet community. TRAPPIST-1 is a compact system of 7 roughly Earth-sized planets orbiting an ultra-cool dwarf star, with several of them sitting inside the star's habitable zone. When it was first discovered, it was treated as one of the most promising systems ever found for potentially habitable worlds, largely because of how many rocky, roughly Earth-sized planets it contains all in one place. But when Webb examined the innermost planets in the system, TRAPPIST-1b and c, it found essentially no evidence of a substantial atmosphere on either one. Both appear to be bare, airless rock, constantly exposed to intense radiation from their host star with nothing left to shield them. That's a meaningful result, not just a disappointing one, because it tells researchers something important about ultra-cool dwarf stars in general. These small, dim stars are prone to frequent flares and intense radiation output relative to their size, and that appears capable of stripping thin atmospheres away from close-orbiting planets over time. The outer planets in the TRAPPIST-1 system, which sit farther from that radiation, haven't all been fully characterized yet, and there's still a genuine chance some of them retain thinner atmospheres Webb hasn't confirmed one way or the other. But the results from the two inner worlds have already reshaped how astronomers think about habitability around this entire category of star, pushing the community toward taking stellar activity just as seriously as orbital distance when judging whether a planet might actually be capable of supporting life. Step back and look at everything Webb has found across all of these different worlds, and a genuinely strange pattern starts to emerge. The galaxy is clearly full of planets, rocky ones, gas giants, planets with oceans hidden beneath thick atmospheres, planets with active chemistry unfolding in real time, planets sitting in orbits that shouldn't be possible according to our formation models. And yet, despite examining atmosphere after atmosphere in increasing detail, no telescope has yet returned confirmed, unambiguous evidence of biological activity anywhere beyond Earth. We keep finding water, organic molecules, complex chemistry, and conditions that sound genuinely promising on paper. We have not yet found a confirmed signature that most of the scientific community agrees can only be explained by life. That gap between abundance and confirmation is one of the more unsettling open questions in modern astronomy, and it's worth sitting with for a moment rather than rushing past it. It also helps to remember just how young the science of exoplanet atmospheres really is when you're weighing that silence. Astronomers have now confirmed more than 5,000 exoplanets across the galaxy, and that number keeps climbing every year as new surveys come online. But confirming that a planet exists is a completely different task from actually characterizing its atmosphere in detail, and Webb is really the first telescope with a combination of sensitivity and wavelength coverage to do that kind of detailed characterization on more than a small handful of especially favorable targets. Out of those thousands of confirmed planets, only a relatively small fraction have had their atmospheres studied with anything close to the level of detail we've walked through tonight. So when people ask why we haven't found clear evidence of life yet, part of the honest answer is that we've barely begun the kind of close molecule-by-molecule inspection that would actually be capable of finding it, even if it's out there waiting to be found on one of those thousands of other worlds we've only barely glimpsed so far. There are a few different ways scientists think about that gap, and none of them is more scientifically respectable than the others right now. One possibility is that life really is rare, and that Earth's own history involved a long chain of fortunate circumstances that don't repeat easily elsewhere, even on planets that look promising from a distance. Another possibility is that life is out there in meaningful numbers, but our current instruments simply aren't sensitive enough yet to detect the faint, specific signatures that would confirm it, meaning the silence we're hearing right now says more about the limits of our technology than about the actual presence or absence of life in the galaxy. And a third possibility, one that gets less attention but is taken seriously by a lot of researchers, is that the specific combination of conditions required for life to actually get started, not just survive but originate in the first place, might be a far narrower target than the mere presence of water and organic chemistry would suggest. Each of these possibilities leads to a different set of priorities for where astronomers should point the next generation of telescopes, and honestly, that's exactly why missions like Webb, and the even more ambitious observatories being planned to follow it, matter so much right now. What ties every one of these discoveries together The crisp new image of ship P65426b, the alien photochemistry inside WASP-39b's atmosphere, the tentative and ultimately unconfirmed excitement around K2-18b, the frustrating inaccessibility of Proxima b, and the sobering emptiness found on the inner worlds of TRAPPIST-1 is that we are no longer just theorizing about these planets from a distance. We are reading their actual light, molecule by molecule, and building real physical descriptions of worlds we will likely never visit in person. Every photon Webb captures from one of these planets has traveled an almost incomprehensible distance through empty space, carrying within it a faint chemical fingerprint of exactly what that planet's atmosphere is made of. There's that a telescope sitting roughly 1 million miles from Earth can now read the composition of a world hundreds of light years away, using nothing but the light that world happens to be giving off. It's also worth remembering just how young this entire field still is. Direct imaging of exoplanets has really only been possible for a little over 2 decades, and Webb has only been conducting science operations since the middle of 2022. In that relatively short window, it has already produced sharper direct images, deeper atmospheric characterizations, and more genuine surprises than most researchers expected this early in the mission. That pace matters because it suggests we're still very much in the opening chapters of this story, rather than anywhere near its conclusion. Future observing time on Webb, along with new ground-based instruments and next-generation space telescopes currently in development, are going to keep pushing on exactly the questions this video has walked through. Can we get better atmospheric data on planets like K2-18b to finally settle the dimethyl sulfide question one way or the other? Can new chronograph technology eventually let us see past the glare of stars like Proxima Centauri? Will the outer TRAPPIST-1 planets turn out to have atmospheres their inner siblings lost? And will some future observation finally produce a biosignature detection robust enough that the scientific community agrees it genuinely points to life, rather than one that fades under closer scrutiny the way K2-18b's initial claim did? None of these questions have easy answers yet, and I think that's honestly the most exciting part of where things stand right now, rather than a letdown. Every one of these planets represents a genuine mystery still being actively worked out, not a settled case, being reported after the fact. Astronomers are watching this unfold in close to real time, revising their models, arguing over interpretations, and occasionally walking back claims that didn't hold up, which is exactly what a healthy scientific process looks like, even when it's less tidy than a single dramatic headline. If you want to keep following along as this story develops, as Webb keeps pointing its instruments at new worlds, as researchers keep testing and retesting claims like the one made about K2-18b, and as the next generation of telescopes gets built specifically to answer the questions Webb has raised but couldn't fully resolve on its own, go ahead and subscribe to this channel and turn on notifications so you don't miss the next update. We'll be walking through every new image, every new spectrum, and every new claim exactly the way we did tonight, with the excitement these discoveries genuinely deserve, but also with the honest caveats that real science requires. Understanding what Webb is actually finding out there takes more than glancing at a dramatic headline for a few seconds before scrolling past it. It means walking through what each molecule detected actually means, what each unusual orbit or unexpected temperature reading genuinely implies about a planet's history, and why scientists respond so differently to claims that might sound similar on the surface but carry very different levels of confidence underneath. That's exactly the kind of careful, patient depth we plan to keep bringing you with every future update, as James Webb continues its mission and inevitably turns up more worlds that challenge what we think we already know about how planets form, how atmospheres evolve, and whether somewhere out among all these newly imaged worlds, life is quietly waiting for us to finally find it.